All right, good afternoon and welcome to our October 1st, 2020 edition of Rocks in the Field. My name is Scott Harris. I am the staff planetary geologist for Fernbank Science Center and the Jim Cherry Memorial Planetarium in Atlanta. And this is the third installment in our Rocks in the Field programming to go along with our Fernbank Rocks and Space Rocks programming in other parts of the week. I would remind you that if you are using this resource for your classes, for your students, for professional development, for any educational reason at all, we'd love to hear from you. If you could please let me know in the comments and chat features in Facebook Live or by emailing me at scott.harris@fernbank.edu. We just like to have that information for our records and know how to support you better. And so today we're going to take a trip here inside of the Atlanta area in southern DeKalb County to a place that we often take students when we are in our normal times. And so we're going to do this trip a few times through the semester, and each time it's going to be a bit different. Today is going to be just walking through and exploring like we would do with the students at Arabia Mountain. And to introduce us to Arabia Mountain, you see part of the mountain behind me. We're going to go over to our presentation just for a moment here. And the first thing we're going to notice is that we are in an area where there are some other famous mountains, particularly up to the eastern border of DeKalb County with Gwinnett County. We have Stone Mountain, a quartz monzonite, or what we call a granitic rock. Some people call it a granite, but as we saw in previous episodes of Rocks of the Field, this is not a true granite at all. It's a quartz monzonite. And as we move down to the south, we find a different sort of rock here at Pine Mountain. I'll show you that in more detail in a second. But this is what we call the Lithonia gneiss. So we have a quartz monzonite here. This is an igneous rock formed by the cooling of magma beneath the ground. Here we have a metamorphic rock, and that's the same thing. In fact, the same Lithonia gneiss that we find at Arabia Mountain here in the southeastern corner of DeKalb County. All of these are what we call monadnocks. They are isolated hills above the plain, and in this case, the plain there above is the Piedmont of Georgia, the Appalachian foothills. And so if we move down from Stone Mountain, we find an area around the Georgia 124 and Interstate 20, the area of Stonecrest Mall. Just north of that mall, we have a number of large rock quarries. These rock quarries have been active for many, many decades. And I want to show you one of those right here that has actually has a monadnock called Pine Mountain, where the crest of that mountain has been excavated by the mining operations for quarrying rock for what we call crushed stone or aggregate. Sometimes, as we'll see, we saw at Stone Mountain, we'll see at Arabia Mountain, these rocks are cut out from the they're cut out from the mountain in blocks and taken for building monuments, actually building buildings, and that is what we call dimension stone. It has dimension to it. Crushed rock is exactly what it says. We take the rock, so we put it in very large rock crushers, and they break the material down into aggregate that is then used as the rock inside of cement, whether that be Portland cement or asphaltic cement. This is the rock that is used to give that material its strength. And so here we see how that is, how that Lithonia gneiss is exploited there for use in building many things, including the concrete pavements on the nearby highways and interstate. To the south of that, we find the Arabia Mountain, which is sort of divided into two halves. There is a western low side here, and then this central portion that is high standing with two sort of mounds separated by a low spot in between. And we will finish today's field trip looking at that lake. Now, when we look at the geology of Georgia, we look at the Piedmont here. We have the Valiant Ridge to the northwest. We have the Blue Ridge, and then the Piedmont, and of course to the south, the coastal plain. This area that we call the Piedmont is composed largely of metamorphic rocks. These are rocks that started their lives inside. Well, they actually started off as a lot of materials, particularly out on the seafloor, maybe a billion years ago, and then successive phases of building the Appalachian Mountains squeezed and pressed and cooked those rocks deep down inside those mountains, and they were changed from whatever they were before, what we call protoliths, the beginning rocks, to what they are now, the metamorphic rocks. And so today, after lots of weathering and erosion of those high Appalachian peaks, we're walking around on the cores of those ancient mountains when we walk outside onto the Piedmont. So we're looking at those metamorphic rocks. Now, sometimes the conditions were right to actually create magmas, and that's what we see with these sort of light-colored pinks and whites here. Some of those granitic bodies, or in the case of Stone Mountain, a quartz monzonite. So where are we with Arabia? Well, we're here in the midst of all of this metamorphic terrain, and we're looking at materials that were cooked and squeezed back about 375 to 400 million years ago, when this piece of continent, the small continent called Avalonia, rammed into the side of North America, as you see there in the cartoon. And so when we look at this area where we find Pine Mountain and Arabia Mountain, these are all part of this Lithonia gneiss that you see here in this lavender color. very distinct from these granitic igneous rocks. And when did this happen? Or again, between 375 and 400 million years ago. This is in the Devonian period of the Paleozoic era. So quite a while back. This is actually before Pangaea, the supercontinent, had fully formed at about 300 million years ago. So as we go through the field trip, some questions that you might keep in mind are, what exactly do we mean by some of these terms? Like, again, what is a monadnock? I've addressed that already, but we'll see that monadnock kind of out there in person. And then, what is a gneiss? Exactly what does it look like in the field? And how does that compare with our granite at Stone Mountain, for instance, or any of the other granites that are intruding into the metamorphic rocks of the Piedmont? And this specific gneiss we call the Lithonia gneiss. How did it form? We've already talked about when it formed, but what was it before? What was the protolith? And can you provide some evidence from the field trip to support your hypothesis about how the Lithonia gneiss came to be? And then let's take a look at some weathering out here. This is an exposed bare granitic. We're going to call this a granitic outcrop, even though it's not granite. We often call, you hear these bare exposures of rock in the Piedmont called bare granitic outcrops or bare granitic knobs, and they're exposed to a lot of the weathering that's out there, right? They're sitting out there all by themselves, isolated. What kind of weathering do we observe? And one of the particular types of weathering we'll see are these solution pits on top of the mountain, and we want to think about how those formed. So to do that, we're going to, I'm going to come back to you just for a moment, and then we're going to go over to our field trip. And again, if you have questions as we move through today, if you're watching live, please put those in your in the chat feature or the comments section of Facebook Live. Or if you want to ask them later, please email me. And if you're watching this later and in recorded version, then please do email me any questions that you have and let me know that you're using this. I greatly appreciate that. So we're going to go over to our field trip now. And we're going to start here by simply at the DeKalb County Park office here at the what's called officially Arabia Davidson Mountain Nature Preserve. We'll walk here behind the ranger's cabin. During the non-pandemic times, this is an excellent place to meet with the rangers and see some interpretive exhibits. There's even a classroom inside for many of the teachers if you ever need to use that. And so the ranger in charge is a great guy named Robbie Askerobi. So look him up. Now we're going to zip up here and we're going to veer off the trail over to a bare exposure of the gneiss. Now you're noticing here we have these hardwood forests here that are very common throughout the Piedmont. We have a lot of the underbrush, and we're going to walk out here onto a bare exposure of gneiss. And it's almost like changing into a desert environment. Suddenly, very little vegetation. The vegetation we do see is very sparse, it's very scrubby, even some plants that you expect to find in a desert. And that's one of the reasons this is called Arabia Mountain, is because the early settlers thought that this was so desert-like that it was like the Arabian desert. Well, not exactly. It's not full of sand, right? But here we see the Lithonia gneiss as it looks on a weathered surface, and we might also notice that this has been quarried and mined. You see some of the walls around that are very sharp, indicating that you have that type of some type of excavation of this material. If we look a little bit closer at the gneiss, where you might notice some crude banding. It's a little hard to see on the weathered surface. And we see minerals that are very light colored. Those are feldspars and quartz, both potassium feldspars and plagioclase feldspars, and sort of the grayish, glassy quartz, just like you would find in a granite. But there's a lot more mica in this. This is one of the hallmarks of metamorphic rocks, abandoned metamorphic rocks like gneisses. There's a lot more of the micas. That's because they start off as clays, and those clays are baked by the metamorphism. And when clays are baked at those temperatures, they change into micas. And those micas here separate from the quartz and feldspar to make this layer cake banded texture that we call gneissic, and that's why we call these gneiss. Now, for those of you who like the life sciences, this is a great place to look at some unique environments. Here's a nice little ephemeral pond, meaning it's only wet after the rain. It collects until that water then evaporates away. But it can provide wonderful habitats for all sorts of plants and animals, like you see there with some of the salamanders. There are little tadpoles swimming around there that are going to become adult frogs. So we're going to take a journey across part of the mined area. We'll notice that later we'll be on a part of the mountain that wasn't mined. And the reason for that is, even though this is all gneiss, what it was to start with can be different. The exact pressures and temperatures it was at can be a little different. And so it leads to differences in how robust that rock is. Some of it fractures very easily. Some of it is better in, for building buildings because it's more rigid and tougher. And so those areas that had very rigid, tough, less brittle pieces of gneiss, those were mined for the dimension stone. Other places, the early miners drilled down and they saw that the rock wasn't as competent. It wasn't as tough. And so that might be material that, well, you just don't mine at all, or maybe some of the material that you would break down and crush to form some of the aggregates for, maybe just the gravel in your driveway. We're going to just venture along here. We want to just pay attention. And if you're a teacher out there tearing your students on this later, observe. Talk about what you observe. Notice the pine trees now. Pine trees do very well on these types of exposures, or relatively well, because they don't have deep roots. They don't need the soft, loamy soil to get down deep into to get water. The pine trees can do very well by spreading out through the shallow cracks. And as they do that, they actually bust apart the rock, creating smaller bits of rock through a process called root wedging. And as they break those rocks apart, they actually break them down all the way to sand. And pine trees kind of like sand. So you have a lot of loblolly pines that form in these environments, both with Stone Mountain and here at Arabian Mountain. Here's one of those places where you can see the sharp context where we had material cut or even blasted away during the mining operation. And we also see these beautiful yellow daisies that are common to these granitic bald outcrops here in the Piedmont in the early fall. Here you see the banding a lot better. All the black that you see in there, the dark gray, that's the biotite mica, the black mica, the iron-rich mica, as opposed to the iron-poor, silvery muscovite. And you can see that tight banding. You see it even better where it's wet, and it gives a little bit better, little bit easier, better view of it as it's kind of cleaned off some of the debris and even some of the rusty material from the surface weathering on the rock. Now, this very, very tight banding is common for what we call banded gneisses. And sometimes you'll hear about Arabian Mountain as being partially molten. You get the sense that it was like, partially molten and like a really fluid taffy-like material. Well, taffy-like, yes, but really fluid, there's really no evidence of that. When we talk about partially melted rocks like this deep in the crust, we could talk about things called migmatites. They're not migmatites here. These are actually just tightly banded gneisses, meaning they were subjected to pretty intense heat and pressure, but they didn't melt. So when we see some of the things that we'll observe a little later, we have to kind of think about these not as pieces dropping off in a magma like at Stone Mountain, but we have to imagine other ways of getting like blocks of material that look like they're wrapped up inside of them some material. We'll see that in just a little bit. we're going to go along here and see that you can have fun with rocks. I always like to encourage students, you know, if you're not into geology, but you're into art, well, rocks are still kind of cool, right? There are some places where I'm sure some young artists decide to come out and kind of have their rock creatures there, those rock people created out of the Lithonia gneiss. By the way, the term Lithonia, I hope you know what that means. The city of Lithonia. Lithos is the Greek root for rock, and that means so Lithonia is the city of rock. So the Lithonia gneiss is the gneiss found in the city of rock, and of course it's named that because of these shallow exposures of the gneiss there in the Lithonia area. Listen to the kind of wind blowing by as we walk, and you'll hear some other sounds that also give you a clear indication that even though this is beautiful nature preserve, we are in an urban environment, and you'll hear some of that. But here's a fold. This is a place where the rocks are so contorted that they're actually bent around. This is again a hallmark of when we see metamorphic terrains. And we see these dark crystals there of tourmaline that are in the rock. We see some of that even at Stone Mountain. The Lithonia gneiss was very, very boron rich, leading to the formation of the tourmaline. And then we see these little red plants. These are diamorpha. These are also very common on these bare exposed outcrops like Stone Mountain and Arabian. They're a very important part of the floral communities that live in these shallow pools, these ephemeral pools, and sometimes these deeper solution pits that we'll talk about later. And of course, we see lichen, communities of fungi and algae living all over the place on these rocks that are exposed to pretty harsh conditions. During the daytime, these rocks can heat up pretty dramatically. Even in the wintertime, there's a lot of the sun's energy that is absorbed in these rocks. But then they lose that very quickly too. It's very much like a desert environment. We notice now in the area that wasn't mined, we see this almost sort of black mat, this black crust across some of the rocks. Those are living organisms too. There are different types of mosses and different lichen communities that compose these crusts. So we often say that when we're walking out in virgin areas where people really haven't been, we want to be very careful about how much we trample on those communities, because many of them contain species that are very unique to these granitic outcrops, and we don't want to disturb them. We'll go through a little bit of the pines here. And we notice that there are even cactus here. These are prickly pear cacti that are here. Both that you may have already seen some of the yucca plants, but the yuccas and the prickly pear are some of the succulent plants that, again, you normally find in desert environments. And that's because, again, this is a desert. It is a very harsh, there's some of the yucca. This is a very harsh environment. Now, when we're out looking at rocks, we have to be careful. If we wanted to name this kind of rock, it looks like a sedimentary breccia, right? It's a lot of angular pieces all cemented together. But what is this? That is concrete. It is cemented together by Portland cement. So there is evidence of some of the human activities out here during the mining operation. Now we're going to see this tight layering in here, but again, this isn't layering. This is called foliation. It's the gneissic foliation, the banding the separation of the light-colored quartz and feldspar from the darker colored biotite micas. This was sediment. This was mud on a seafloor that was squeezed and pressed. And this was probably very, very silicious mud, kind of shaly muds like we find around most continents today. But there were some other things that were being deposited on that seafloor. And we see some evidence of it here with this very tight fold, again showing you the compression. But over to the side, you might notice there's also a little broken material. But notice how this kind of looks red. It's red because it's full of garnets. If we want to be technical about it, this is a perluminous composition. And you see a piece of a fragment of rock there, called a xenolith, really, that is inside the gneiss too. But this isn't like a xenolith falling into a magma chamber like at Stone Mountain. These had to be rocks that were out on the surface of the mud. And this mud, that now has transformed into the garnets, that probably was felsic ash, material from one of those stratovolcanoes or even a super volcano eruption, throwing ash up in the sky, it falling down on the ocean floor. And maybe there were even some chunks of material. That's probably what that xenolith was actually a big piece thrown out of that volcano that landed there in the mud. Some of these other blocks in here also are probably the same as that. We also can see, now we see the garnets and some of the biotite micas up close, but we notice this folded pattern up on top of the rock. So it kind of shows you how these folds look in 3 dimensions as we move around them. Again, evidence of incredible compression during the Akkadian orogeny, the third of the 4 major phases of Appalachian mountain building, again happening between about 375 million and 400 million years ago. So we're seeing a lot of that typical gneiss here as we go along. But keep your eyes open for some other things. See if anything doesn't look like that foliated or banded gneiss. What else could be out here? You notice the vertical pipe-like features that come down in the rock. Those are from drilling. There are 2 purposes that drill holes were made in the rock. One was to test the rock, to find out what kind of rock it was and how competent it was, and whether you really wanted to take the time to mine it. The other were some of these were for actual dynamite, put the dynamite in, and some were just part of drilling to actually just pry the rock apart. So we can see some of these ephemeral ponds again, not quite so deep as the last one. But if you look carefully in these, you'll find some of those little tadpoles roaming around. Here we see some of that incredibly fine banded gneiss. You see another area with that sort of reddish layering for where the garnets are, probably again indicative of some of those ash falls that were falling out in the ocean basin, layering in between the mud that was being supplied by erosion off the continent. The rivers taking that material out to the seacoast, and that mud making it out to deeper water. We also see some xenoliths in here that look like big blocks, and I suppose that those are like boulders that never wore down before they were covered by more mud. You know, you see that on coastlines today where there are kind of big rocks that have seemed like they've been, rolled down the rivers and they wind up there in the mud. Listen overhead there as you hear the jet aircraft on its landing path into Hartsfield-Jackson International Airport. Again, some of that proof that we're in an urban environment. But here's some of those xenoliths you just saw that are like blocks. And this was not molten, so this is not a place where this material fell in from the walls of a magma tube. So those must have been either materials thrown out of the volcanoes and landing, or maybe just boulders that they could even be boulders of mud that at the time, but then they have changed in the same metamorphic event that made all of the mud turn into gneiss. You see more of the diamorpha here filling in some of the pits. But we want to keep our eyes open again for some things that are not metamorphic, not gneiss at all. Well, I'm sure they're nice rocks in the NICE version of the word, but as far as GNEISS, the metamorphic gneiss, we have some things that definitely are not nice up here around the corner. I want you to use your eyes looking for different textures and see if you see something quite a bit different. Does that look like gneiss? It looks more speckled, doesn't it? It's not banded, it's speckled and it's dark. What is that? There's looks like more blocks of it over here. Right in the center, you see another one of those dark rocks. You notice that they have different textures. You see there's some pieces of gneiss, but again, there's that dark thing that looks kind of like speckled. Kind of like almost like a Dalmatian dog, right? We see that spotted texture. What's that indicative of? That's a granite. That's actually a very, very mafic granite, very iron and magnesium rich, that we might even call a tunnel. This has a special name called a tunnelite. That dark material is actually, could be some pyroxenes, iron-bearing pyroxenes, or either iron-rich hornblende or amphiboles. But this one's even different. This has these big crystals of feldspar and plagioclase feldspar at that. And big crystals of microcline, the pinkish feldspars. What's going on there? And then here's one that's sort of gray. That looks a bit like Stone Mountain. That's actually the Elberton granite. And those that are pinkish with the big crystals of feldspar, like we're looking at here, these are pieces of the Danburg granite. Elberton and Danburg are other areas of Georgia where granite was mined. True granites. Well, let's say true granite. They're actually granodiorites. That means that they have hornblende in them. And the granodiorites were mined. Here's a piece of the Danburg granite. And so why are they here at Arabia Mountain? Well, the mining company had like a showroom out here. This is what the rangers call this. They call it the showroom area. This is where the company brought in granites and gneisses that they were quarrying around the state and showed them to their customers. So they have their big blocks of these granites, these granodiorites, quartz mondanites, and such out here in this area. So be careful. And as always, when you're looking at areas, any geologic area, you're looking at the rocks, always keep in mind that people have a major influence on what you see sometimes. So you have to be careful with context. I've been out in the middle of forest, 50 miles in any direction from any living soul, any city, any kind of evidence that there have ever been people there. And I found slag, iron, things made in iron foundries by people. How did it get there? Some people will find these and they'll think, oh, I've got a meteorite that fell out of space because I'm so far away from everybody. And it's like, no, you have to realize that there's very little, particularly of North America, there's very little of the land that has not been touched in some way by people. So as geologists, we have to always keep that in mind. So we're leaving the showplace area here, and we see some more of those very, very fine foliations, the banding there in the gneiss. And we're going to see one more of those ephemeral haunts up ahead. A lot of the rock that's broken up here was broken because of mining operations, but that's a type of weathering, right? That's human weathering, or we're part of the biology of the surface of the planet, so this is what we call biomechanical weathering. Whether it's us or the tree roots busting up the rock, making it smaller, that is biomechanical weathering. There's other types of weathering that are active on these outcrops as well, and we're going to talk about that when we're on the other side of the mountain that we'll be to in just a little bit. But think for now what other types of weathering there might be. You notice all the water out here running along doesn't really look like it's changing the surface very much, right? I mean, just the action of water running along, the wind blowing over the rocks, where there are other environments on the planet where those make a big deal in terms of breaking the rocks down and moving them, or what we call erosion. But here, that really doesn't do a whole lot. There are areas here that probably look very, hardly different than they did hundreds of years ago, thousands of years ago. Just millimeters of material, even if that, changed by the water and wind running across these. But that mechanical weathering or biomechanical weathering from the tree roots, even the grasses and the mosses, that can make a big deal. But there's something else that those mosses and lichens do it's even more important. We'll talk about that again, as I promised, on the other side of the mountain. Excellent place for frogs to lay their eggs and for tadpoles to hatch out and mature into new frogs. So now we've crossed the road. This is across Klondike Road at the park, and we see an area that we see a lot of more areas that aren't mining. We're going to see some that are, but remember those areas that you don't see the mining probably are where the rock was tested and it was too friable, too weak to really be mined as dimension stone for building monuments and even houses. So we're going to run quickly up the mountain here. And as we go up the slope, I'm going to pause right here so that we can see this sort of slab of rock. It looks like it's sort of sliding down at us, right? These cracks that are sort of parallel to the surface of the mountain, that horizontal crack, those are special cracks we call joints, and particularly exfoliation joints. These cracks are where, as we erode material off the top of the mountain, the pressure is relieved and the rock sort of pops open. It's like unpeeling an onion, right? You unpeel an onion, take one layer off, the next layer pops open. That's what's happening here, and that's a process called exfoliation. That is a unique way in which these granitic and granitic gneiss outcrops physically weather or mechanically weather over time, and it's what's responsible for giving them this sort of domed shape. Just like the quartz monzonites at Stone Mountain, the exfoliation takes whatever the original shape of the rocks, shapes of the rocks were, and it sort of develops this dome shape over time. Now we see all these little pools. These are called solution pits, and that's short for dissolution, a chemical process. You're dissolving stuff. What are you dissolving? Well, it turns out that our rainfall is naturally slightly acidic. In our air is carbon dioxide, and so the carbon dioxide combines with water vapor in the air to make carbonic acid. That's the same acid that weathers your teeth, right? That's in soda. And so that acid attacks the feldspars in these rocks. And a little bit of the acid starts weathering away, chemically weathering away the feldspars, a little hole. Well, that little hole opens up and more water can get inside, more acidic water, so a greater surface area. And so we get more chemical weather. The more surface area we get, the more efficient that weathering is, the bigger the hole we make. The holes get big enough, they become communities for the grass and the moss and the lichen. And as those organisms live, as those lichen and mosses in particular, as they live out their lives, they die and decay, and the decaying organic matter creates some acid. And when they're alive, they secrete waste, and their waste is acidic. So now you have acids from them excreting, you have acid from the rain, you have acid from the decaying organic matter when they die, and that acid continues to attack the feldspars, turning it into white clay that we call kaolinite, and that soft white clay, then the rain can just take away, leaving these bigger and bigger holes. And the bigger the holes are, the more area you have for these communities to develop. Sometimes you'll hear people claim that these are created by lightning strikes. No, lightning has nothing to do with it. I can't say that the top of a bare mountain like this doesn't get hit by its fair share of lightning, but that's not what causes these holes. Now, you might notice on the horizon there, looking off to the south of Arabian Mountain, you see some other little monadnocks. One of those monadnocks, or a couple of them there in the distance, those are part of Panola Mountain. Panola Mountain is one of the other monadnocks in the area, and it is made of granite. It's really more of a granodiorite, like most granites on our planet, but it's distinctly different from the metamorphic rocks in Arabia, and distinctly different from Stone Mountain's quartz monzonite. Panola Mountain is a different granite that was formed actually at a different age than even Stone Mountain. Probably formed a little bit at a time a little bit older than Stone Mountain. We're going to get to see what this gneiss looks like on very fresh surfaces, where some of that exfoliation is actually popped open some of the pieces, and probably people then turn them upside down, and you can see that white feldspar. Those are particularly the albite sodium-rich feldspars, along with probably some sodium-rich plagioclase, and even some white microcline potassium feldspar. But you saw the little bands of the black biotite mica in between those. Now, one of the things we talked about here is um, these were fine muds out on seafloor for the most part, maybe with some ash falls in between the mud layers. And so as we think about that, think about what changes we could find. Would we expect to see all of that mud being, well, just mud? Or what if sea level changed? Would there be coarser material or finer material deposited? I mean, what if the sea level actually got lower and you were closer to shore? The rivers could bring more sand out, right? Rather than just the mud, or even bigger pieces. If you get bigger, like pebbles, you create conglomerates. And then the sand would form sandstones, and the mudstone. And the mudstone, again, we talked about when it's heated and pressed, changes into this very, very finely banded gneiss. But could we find some of those other materials out here? What would they look like? I mean, what would you expect to see if you had coarser sand or even little cobbles in a conglomerate? And they got caught up in that squeezing and heat and pressure from the mountain building. Well, notice there's some rocks out here that look like they're standing up pretty well to the rest of the weathering, both the mechanical weathering and the chemical weathering. Some of these blocks look pretty rugged. What's different about them? Is there something fundamentally different that makes them a little tougher? Look at the foliation here. Notice it's not as fine, and you actually have what's called differential weathering. You have the finer micas coming out, weathering away. And if you look underneath here, notice that maybe you see this looks coarser. This is actually probably was a coarser sandy material, or even a conglomerate. So we have now a meta sandstone or a meta conglomerate at the base of some of these big boulders. So this is sediment that's not just mud. There's some variation in it that you can try to observe. See this very, very coarse material. Some of this material almost looks like, it is probably not, but it almost looks like cross bedding you'd find in a sandstone. Most of the time that doesn't survive the intense metamorphism that these rocks have seen, but sometimes it does. And certainly at places with lower amounts of metamorphism, you can preserve the original sedimentary structures. But it'd be interesting to look more closely at these rocks to determine exactly what their protoliths were like. That before rock, that sediment that existed before the mountain building occurred. And just remember that we're talking about metamorphism going on miles down inside the Earth's crust, right? So over the last, hundreds of millions of years, 300 million years since Pangaea was formed, all of, if we were here when Pangaea existed 300 million years ago, we'd be standing under 5 to 8 miles of rock. Where's it all gone? It's weathered and eroded away. And all of those mountain peaks, well, they make up the coastal plain today. All that sand and mud in the coastal plain came from the erosion of those high Appalachian peaks that were formed back in that 300 to 400 million year old, 3 to 400 million year time frame. Now we see the lake that we saw from the air at the beginning, and we see these little ephemeral streams. There's ephemeral ponds and ephemeral streams, but these ephemeral streams actually feed a pretty permanent pond there. Actually, a typical sort of Piedmont pond there that you would expect to find pretty decent populations of things like fish. There are bass in there, brim, bluegill brim. You see some I talked to those folks. Those are some former DeKalb County students from Arabia Mountain High School there that are playing there on the lake shore. some of that more coarse material. Now, as we end our trip, we're going to go back up to the top of the mountain. We'll take a quick look back here at the pond, just to get a little bit of a closer view. But now we're going to look at the waters feeding this pond as we go journey up one of those ephemeral streams. And we see it's beautiful this time of year with the yellow daisies. And we see the water cascading down from the top. Of course, as you see that water moving along, it does, in small areas, wear into the rock, helping deepen those little channels. But imagine this has been going on for millions of years. And it really doesn't dig down that deeply. So, you know, that type of erosion by flowing water on a surface like this happens very, very slowly. Most erosion on our planet is actually really fast. It's like from flash floods and landslides and collapses. Just that day-to-day grind of the water over the surface, yes, it changes things, but very, very slowly. You might notice along some of the sides of these little ephemeral streams or streamlets, you see some white incrustations. Those are from some of the chemical materials that are carried along with the water. When that acidic water chemically weathers the rock, you have ions that go into solution, like sodium ion, calcium ion, and it has to go somewhere so the waters carry those away. And when they get to the right conditions, they might reprecipitate out some of these white incrustations. There might even be calcium carbonate or calcite that you would find along some of the edges of these streams, just from the reprecipitation of that calcium with dissolved CO2 in the water, forming carbonate ions. You get the calcium and the carbonate, and you make a little bit of calcite. So we're coming back up onto part of the mountain that was mined. You see some of the fragments from the cutting and perhaps even blasting that occurred. As we get to the end of our trip today, I hope you enjoyed your virtual tour of Arabian Mountain. Learned a few things about weathering and erosion, and mechanical weathering versus chemical weathering. What a gneiss is, what the Lithonia gneiss is, and how it formed from those sedimentary protoliths, maybe even with some volcanic ash, creating a few of those layers. So we're going to get up here to one of those little show places again. One of those areas that was mined out, and some of the rocks demonstrated to customers of the mining company. And so that's where we end today, here at the top of the eastern side of Arabian Mountain. So thank you so much for joining me. I hope you found this useful, either live or in its recorded version. If you do have any questions for me, please do put them into the chat feature or email me at scott.harris@fernbank.edu. Hope you have a wonderful remainder of your week, and see you next time when we will, let's see. I'll have to update everyone later on exactly what we're going to be touring next time. But this series is going to continue throughout at least the fall, and I hope far much further than that as we explore some of my favorite places, not only here in Georgia, but around the world. See you next time on Rocks in the Field, and also see you next Monday for Space Rocks, and the following Tuesday for Fernbank Rocks, where we will look at in detail at metamorphic rocks. Thank you very much for joining me. Bye-bye.